Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today I would like to discuss about the special type of CRO, cathode ray oscilloscope. This material is the next chapter after we talk about the oscilloscope in the chapter 4. So in this chapter, I would like to introduce you many types of CRO. The first one of the CRO is dual beam CRO. You can see from this figure that we have two beam of CRO. The first one is the beam 1 here, and then the second is the beam 2. And we can see we have a two input here. This is the Y1 from the input A and Y2 from the B input. And Y1 and Y2 has a similar blocks after the input signal. There is an attenuator and then vertical amplifier for A input, and then attenuator and vertical amplifier for B input. And both input input A and input B is going to the similar synchronization circuits as we already talked in the previous chapter. We have a synchronization circuit, time-based generator, and horizontal amplifier. So in front of the vertical amplifier, usually we see a delay line here. Delay line is here, and this is in this dual beam CRO. They didn't provide a delay line here, and then the vertical amplifier A is coming to the beam 1 and vertical amplifier B is coming to the beam 2. We using the select the switch here. We have the 3 switch from each amplifier, and then we also have an external horizontal amplifier for another horizontal amplifier. We have two horizontal amplifier here. The first one is coming from the synchronization circuits, and then the other is from external horizontal amplifier from the external circuit. The function of the vertical amplifier and horizontal amplifier is similar with the conventional CRO. So the vertical amplifier is used to amplify the y-axis, while the horizontal amplifier is used to amplify the x-axis. And we can see here the CRT has two electron guns and then two independent deflection plates. And if we want to check the characteristic of the signal, maybe we can use this dual beam here. On the one channel is used to show the phase shift between two sine wave signal, and then another we can see the time variation, so we can display in simultaneously using the beam 1 and beam 2 if we have a two sine wave signal. And then we can also observe if we have the slow and fast signal, and if we have the low frequency signal and high frequency signal, we can show in this dual beam CRO. Okay, and then a similar signal can also observe by giving the signal to Y1 and Y2 input. So we can sweeping the signal at a different sweep rate. So we can compare anything using this dual beam CRO from one signal. So this is the advantage of the dual beam CRO compared to the single beam CRO. And then the other type of the CRO is the dual trace CRO. The previous I talked about the dual beam. So dual beam have a two beam or two screen. So in dual trace CRO we have only single beam, single time-based generator, and then we have a two identical vertical amplifier with the electronic switch. Also, we have the single beam CRT, but in this dual trace, we have a two separate vertical input signal. So we can see using a two vertical input signal using the one single beam CRT, we can observe two vertical input signal simultaneously. So we have two modes of the operation. The first one is alternating mode, and then the other is the cope mode. This alternating mode and cope mode, you can check the detailed explanation in the textbook. Then after we talking about the dual beam CRO and also dual trace CRO, the important thing in special type CRO is the sampling oscilloscope. If we want to check or observe the vertical high frequency signal, so the writing speed of the electron should be increases, because in this case we deal with the high frequency signal. So if we increase the writing speed of the electron, the image intensity will be reduced. So if we want to maintain the intensity on the image intensity in the screen, so we have to accelerate the electron to the higher speed. Hence, the accelerating potential is to be increased. Why? Because we want to accelerate the electron, we have to increase the accelerating potential. However, if we increase the accelerating potential, the deflection sensitivity will be decreases. So to maintain the similar sensitivity, the deflecting potential must be increased. Therefore, the vertical amplifier needs to be redesigned and modification are to be made. So if we deal with the very high frequency signal, we have to redesign the vertical amplifier if we don't have a sampling oscilloscope. So in these situations, we use the sampling oscilloscope if we have or we change the frequency signal, so we reconstruct the waveform, so the image intensity and also the sensitivity will be maintained. So we can see we have the input waveform here. We have the inputs waveform here, and then this one is sampling pulse. Sampling pulse is if we want to sampling the input waveform, if the waveform is changed, the frequency is changed, so the sampling pulse will detect this changing, and then to generate the sampling pulse, we need a trigger pulse here. So after we get the sampling pulse and we get that the input waveform is changed, the frequency of the input waveform is changed, so we will reconstruct the waveform. So the image intensity and also the deflecting sensitivity is maintained. We can see here if we this is the signal that from the input, and then using the sampling pulse we sampling the signal. Then if the frequency signal is changed, so the deflection of the horizontal deflection will be changed, like this one, because the first one is here and then it increased to here. So we have to reconstruct this waveform by using the sampling, by using the block of circuit to maintain the intensity and also the sensitivity of the circuit. So this is the sampling circuit. We can see here this is the input signal, and then this is the sampling gate. The sampling gate is coming from this block, we have the trigger input, blocking oscillator, ramp generator, and then also the voltage comparator to compare between the sampling. So we get the sampling pulse, and then the sampling pulse will go like this one. This is the sampling pulse, and then the sampling pulse will sampling the input waveform. So the characteristic of the vertical amplifier will be changed if the sampling rate of the sampling signal change. So we can maintain this vertical amplifier here by using the sampling circuit, and then we can maintain the sensitivity and also the intensity of the image here. And then this voltage comparator is also scanning from the horizontal signal, and then this is the vertical signal. And then if we increase, or if we design the high frequency CRO upon 1 megahertz, so it will be suffer from this following: poor sensitivity, low brightness, and also small CRT display area. So in this situation, we need a sampling circuit. And what is the sampling circuit? So we can see here, this is a resistor here, and then we have this supply switch here, and then this is the capacitor. The capacitor is very useful here for the sampling, because if we have the input signal coming from here, this is the input signal, and then when the input will be sampled in this circuit, if we turn on the switch, so the signal, the input, will be stored in the capacitor, in the CS capacitor here. So then we turn off the switch, and then the capacitor will be distribute the sampling to the circuit, or discharge the sampling signal to the circuit. So we got the E-sample here. So we can see the efficiency of the sampling by using this one. This is the voltage on the CS, the capacitor CS, after each sample, or E-sample, and then per input voltage. So we can see that if the E-sample is similar to the input voltage, so it means that the efficiency will be going to 100%. And then if we use the low frequency use, so the efficiency is VL, low frequency use dot E sampling is must be 0.05 EI, or 5% of EI. So this is the situation, or this is the construction of the sampling circuit. We use the CS to store the input signal, and then it will be discharged the signal to the sample. And then this is the sampling of the input signal for the vertical amplifier. Is little bit similar. We have the CI here, and we have the CS here to store the signal, and then to sample and then the sample going to this one, to the vertical amplifier. So this is another sampling system. This is for CRT, this is for horizontal amplifier, and then this is the vertical amplifier. And then if we combine the sampling circuit in the vertical amplifier and also the horizontal amplifier, it will be like this one. We have the input signal here, and then this is sampling gate here, and then this is for horizontal amplifier using the similar sampling gate here, voltage comparator. And then we got the vertical signal, and then we got the horizontal signal. And then this is, for example, this is the input waveform, and then this is the sampling pulse. The sampling pulse will sample the input waveform, and then discharge, and then distribute the sample to this input sample to the vertical amplifier, and then we can see in the vertical signal and also the horizontal signal. So this is the sampling oscilloscope, the working principle of the sampling oscilloscope. So I think this is all. This is the three type of the oscilloscope. We already talked about the dual beam CRO and then dual trace CRO, and then we also use the sampling oscilloscope here. And this is very useful, the sampling oscilloscope, if the frequency of the signal changes in the oscilloscope. So we can maintain the intensity and also the sensitivity of oscilloscope. So I think it is all of my presentation. Thank you and good morning.